Hello everybody and welcome to section 4. We're going to be covering absolute age, exact numerical ages of rocks. And the question that we're going to be looking at is our question from the first lecture. How old is the Earth? And how do we know how old it is? How can we be so sure? What is the level of confidence here? How do we get to 99.9% confidence on our estimation? Our absolute age for the Earth is, and you've heard this, 4.56 billion years old. And here is how we know this. First, we looked at things like the saltiness of the sea. Could we figure out how quickly, looking at rivers, that salt goes into the sea, and look at how salty the oceans and the seas are, and work backwards to figure out how long the rivers have been flowing? There's this idea with Darwin. If we know how quickly different species reproduce, how big a generation is, we look at how many species there are on Earth, and we figure out a rate of evolution, maybe we can work back through all of that to the beginning of the Earth. And he estimated about 300 million years based on his understanding of evolution as a slow process. Kelvin used the loaf of bread method, uses thermodynamics in order to estimate the age of the Earth based on how hot the inside might be and how quickly it might have cooled. And finally, John Jolly used Halley's method and tried to come up with an age for the Earth, actually putting this into practice, said something about 90 million years old. You might notice something for each of these, which is that none of these are anywhere even remotely close to 1 billion years old, let alone 4.5 billion years old. Let's talk first for a moment about what the oldest rocks are in Arizona. I take a moment to think about where these might be. So, as you might have guessed, these are 1.75 billion year old rocks which are exposed at the bottom of the Grand Canyon, Upper Granite Gorge. We would talk about a subunit of this called the Brahma Schist, which gives us that 1.75 billion year old figure. And there are some other rocks in Arizona which are almost this old, all around Arizona actually, and some specifically in the White Tank Mountains. You can see this Brahma Schist, this material right here is what we're looking at down here at the bottom of the canyon where the oldest rocks are found. But what about the oldest rocks on Earth? Are these going to be 4.56 billion years old? Are they going to be more like 2 billion years old? Something in between? Well, older rocks are going to be subject to many, many more generations of being folded and moved and eroded and broken and messed up and cooked and altered. So the older rocks, for the most part, are gone. The further back in the record you go, the less of a chance there is that something could have survived for so long. Because of this, the oldest rocks that we have on Earth are only around 4 billion years old. These are metamorphic rocks. Is called a gneiss, found in northern Canada. But it still doesn't get us to 4.56, so that can't be how we figured it out. You can actually see an example of this, our little gneiss here up in the north of Canada. So how about the oldest minerals? Well, there are these zircons, little indestructible uranium-carrying zircons, which we find in sandstones in the Jack Hills in Western Australia. And these are 4.36 billion years old, but this still doesn't get us to 4.56. How does that number get to be here if we don't have any rocks there, we don't have any minerals from this time period? How do we get to 4.56 billion years? You can actually see a little bit. Here's our zircon here. Here is the Jack Hills in Western Australia. No, I don't think that it actually is this blue color, but definitely much easier to see what's going on inside the crystal this way, the little layers where it's grown. So here is our full timeline of folks trying to answer this original question, how old is the Earth? Everything from Halley, looking at the saltiness of the sea, all the way up till here. The 1950s, Claire Patterson looks at the age of the Earth as being 4.56 billion years based on radiometric dating of a meteorite. This estimate is still considered to be pretty close. What is the oldest solar system material we could look at? These are our meteorites. I remember from our other lecture we talked about this dispersed cloud of space dust. It comes together and starts spinning around in a disk. The sun ignites all the stuff which is closest to the center, blasts everything outward. Material starts spinning around the sun. A lot of it does condense and coalesce into planets, but some of it does not. Remember, some of it becomes the asteroid belt. Some of it is still leftover primordial solar system material which never became a planet and which has not experienced anything to alter it since. These are our meteorites, which sometimes visit us on Earth, sometimes are preserved here. These are unaltered material from the beginning of the solar system. So, if we can figure out how old these are, we figure out how old the solar system is. And since we believe the planets in the solar system formed at about the same time, if we know the age of these meteorites, then we know the age of the solar system, and then we know the age of the Earth. Using radiometric dating, which we'll talk about more in a little bit, we get this number, 4.56 billion years. So this is what these meteorites actually look like here. You can see it is kind of a mess. It has all of these little inclusions in it. So these are called chondrite meteors, and these little things are called chondrules. I believe these are aluminum silicates, things that look like rocks that you would find here on Earth, included inside of the meteorite. You might want to watch this video if you'd rather hear these folks explain radiometric dating instead of me. I take no offense. The way radiometric dating works is you have a radioactive product here and a radioactive parent over here. So we start out, it's all parent, the entire thing. This might be some radioactive element. You can think of uranium, but there are a whole lot of others that it could be. And when we start out at our time 0, where 0 half-lives have passed, half-life being the amount of time, and then it starts to decay. The decay is where the parent becomes the daughter. So over 1 half-life worth of time, if we go and we look in the rock, we would see 50-50 between parent and daughter. After 2 half-lives, well, it only goes in one direction. So some of the parent has continued to become daughter, but the daughter stays daughter. So we would have here 75% daughter and 25% parent. And we would keep doing this 3, 4, 5, 6, 7, 8 half-lives until it's almost all daughter. But the nice thing is that we can go back and look in the rocks. We find a rock, we look at the radioactive materials inside of it, and we look at the proportions between the daughter, which we know, and the parent, which we know. And maybe we see that it's here. It's about 95% daughter and about 5% parent. Well, this is the same process no matter which element it is. So based on this and using a graph like this one, we can work backwards and say, okay, well, about 95% daughter and 5% parent. We could say that this has been about 5 half-lives. And since we know how long a half-life is in terms of years, we can use the proportion of parent to daughter inside the rock to tell about how long it has been since that rock has formed. And the half-lives for these, some of them are a long time, anywhere from 500 million all the way up to something like 100 billion years. So there's plenty of parent and daughter left for us to be able to look at. We don't just have to look at something which is almost all parent or almost all daughter. What are the big ideas for this unit? What are the ways to date rocks? What are our 3 ways of looking at the age of rocks? Absolute age, geologic age, and relative age. What are our 6 principles of stratigraphy? Good to know all 6 of these. What is an unconformity? What are the different types? What do these look like and what do they mean? And finally, how have we gotten this number for the absolute age of the Earth? What are the different ways we have looked at? What is the evidence that we have used to form this? That's all.